I'm going to start off with something pretty simple, and that is this is a science experiment you can do at home. I've got a hair dryer. This one has the cool mode so it doesn't get too hot while I'm doing it. And I've got a ping pong ball, and I'm going to... Amazing, all right? What I really like is when you tip it. Okay? Now, if I was a magician, I would say I was doing levitation, right? Levitating it. In the only difference between a science show and a magic show is I have to explain the tricks, right? So when I'm blowing this hair dryer, the air curves over the ball and some of it goes down, and that gives lift to the ball and brings it up. It's called the Coanda effect, and this is part of what makes airplanes fly. I've got a little piece of paper here, and if I take my hair dryer and blow it across, I give it lift. Another thing I could try is I've got a... What's that? Doesn't seem to be working. Is the sound turned down in here? Maybe we could check that. The sound might be off. If I take a tube and I blow across the top of it, I should produce low pressure here, and it'll drag the air up and out. Kind of hard to see that, so we'll put it in some peanuts here. So there is hey, that works now, okay? Sound, that's another part of physics. There's a real-world application to this. Paint sprayers, some paint guns work. The tube goes down in the paint. You blow air across it. It brings paint up and shoots it out, all right? So now that's all cool. You do it small like that, but we could make this a little bit bigger. You know, we're here at the university. We've got a big auditorium. We could do this on a grander scale. So I'm going to try a bigger blower this time, all right? And we'll try a larger ball. Got you. Can you put that back up there? Where's the air going? Is the air hitting the bottom of the ball or going over the top? It's going over the top. Yeah, just like the ping pong ball. It's going over the top. That what makes it stay up. We got something else we could try with this over there in the corner. So you know, this would work with the peanuts, but let's try something else. This is my wife, Alenda, and she's helping me out today. All right, so toilet paper. There we go. I don't know if any of you in your youth ever did any toilet papering. That's something that we do here. You could use this method to toilet paper, but you would lose the element of surprise once you fired up the leaf blower, right? I think they'd find you. Okay? Thank you. It's a hot day today, so I thought we would next do something really cool. And what I've got is I've got liquid nitrogen. Now, nitrogen is not a rare substance. In the air you're breathing, more than 75% of it is nitrogen. Okay, so you're breathing lots of nitrogen, and this is liquid nitrogen, so it's very cold air, basically. And I'm going to take this and dump it into this dewar. Now, you can see that there are two walls to that, and it's been evacuated. The air was taken out of the middle, and so it's like a thermos, but it's clear, so you can see what's going on inside. Now, liquid nitrogen is about 300 degrees below 0 Fahrenheit, and at this container is very hot, and so it's boiling like crazy. You can see it boiling there. So let's let it settle down a little bit. As it cools off the inside of the container, it'll quit boiling mostly. And then we're going to try a few things here. All right, so I've got a balloon, and you think about what makes a balloon stay inflated. Now, there's atmospheric pressure pushing on the balloon. But on the inside of the balloon, there's air pushing out. And that air is actually, you can think of it as a little BB. It's cruising around. It hits the side of the balloon and bounces off. That's what keeps it inflated. The temperature of the air is determined by the average velocity of the air molecules. So if they move fast, it's hot. All right? When it gets hot in this room, that's because the air molecules are moving faster. And they bounce off of you and provide heat also. Question? I can try. Thank you. All right. I tend to have high speed. Sorry about that. So the air molecules inside of here are moving almost 1,000 miles an hour. All right. In the room, air molecules are moving 1,000 miles an hour, but they bounce into another one and another one and another one, and they just keep bouncing. Now, if I cool them off, I should slow them down. So this is just air in this balloon, and as I stick it in the liquid nitrogen, the air molecules will move more slowly, and the pressure goes down, and actually I can liquefy the air because I have liquid nitrogen at this temperature. Oxygen is a liquid. Carbon dioxide, that's a solid at this temperature. That's dry ice. And so all of the air is still in the balloon, but I've converted it into liquid or solid. All right? Now, as it starts to warm back up, they will go faster. Okay? All right, let's stick that in there again. Now, I was doing demonstrations to a group of high school students, and you know how creative high school students can be? Somebody said, what would happen if you tied a knot in the balloon? Okay? So all the air is down there, it's liquefied. I'm going to tie a knot right here. You expect it to pop? Yeah, so do I, and it'll pop loud. I'd plug your ears. The suspense. I don't know. When I least expect it, it'll go, okay? There it went. Let it warm up. All right, now let's try a couple other things here. I told you that oxygen is a liquid at this temperature. Well, I'm going to put a little bit of liquid nitrogen into a can here. Can has metal. Metal's a good conductor. And so you'll see it looks kind of frosty. As it cools, all of a sudden it looks wet. Now that's not water, because water is a solid at this temperature. It's actually liquid oxygen. And you can hear it drip. Okay? Dripping liquid oxygen off the bottom of it. Oxygen liquefies a little higher temperature than nitrogen, so it takes the oxygen out of the air and drips it off. Now, that's boiling inside. Is it a good idea to put a lid on a boiling container? Of course it is. All right, we need more liquid nitrogen. Let's see here. Let's try something else. I've got a container here with water in the bottom of it. I'm going to add some liquid nitrogen. Now, what you see is water vapor. Okay, this isn't nitrogen. That's a cloud formed by that cold liquid nitrogen. And I found one day that a ping pong ball fits perfectly in there. And then if I put my thumb over this... Good catch, good catch. Okay? More liquid nitrogen. I have a bouncy ball. Nice and soft bouncy ball. For this next part, I need to put a glove on. Yeah, I do. Thank you. Just here's fine. Yeah, that goes in the bottom of it. All right, so I'm going to take this nice, soft, squishy, bouncy ball, and I'm going to put it in the liquid nitrogen. Hold it down in there. Roll it around a little bit. So at this temperature, the material this is made out of behaves a little differently. Okay, let's see if it's ready. Glad you sat in the front. Yeah, it broke. It became like it'll be cold right now. Wait for it to warm up, okay? Because it'll be really cold. All right, so we're pretty good here. All right. Liquid nitrogen. Let's see if we can sit that off the side. All right, now the next thing I'm going to do here, I've got some balloons. So of course, if I've got balloons, you've got to have nails, right? Because balloons and nails go good together. Here's a bed of nails. There are 91 nails on this board. The nails are about 1 inch apart. Okay, 91. Now the next board I have has the nails are 2 inches apart. There are only 19 nails on this board. Okay, and the last one I like to call this a bed of nail. It only has 1 nail, okay? So now if I take and put the balloon on the nail, can you predict what will happen? It's going to pop, right? Now how hard will I have to push to get it to pop? 1 nail, probably not very hard. If you notice, if I push hard, I flatten the balloon, right? The harder I push, the flatter it goes. So you can tell about how much force I'm putting on it by how flat it goes. Not very flat. All right, let's try another one. Thank you. So we'll try the one with 19. Now, if you think about it, if it took, say, a pound of force there, and I've got it on 5 nails or 10 nails, it might take 5 or 10 pounds of force to pop this time. Still popped pretty easy, though, didn't it? Now we try the one with 91. A bed of nails, if you've ever seen anyone that lays down on a bed of nails, they're about this distance apart. So if we take this balloon, there must be one sticking up today, but it flattened quite a bit, all right? So if you want to actually have a bed made out of nails, you find out how much it takes to hurt, and then you have enough nails that your body's weight is spread out over all of them, and it doesn't pop. You got one more balloon for me over there? All right, so I've got a big nail, and we'll take this and we'll stab it in here. All right. There we go. Okay. Yeah, that's a magic trick, right? What's the physics in it? What's the science behind it? Well, you notice I've stuck it right at the top and right at the bottom, where if you look at the balloon, there's some extra material, some extra rubber there. And so when I stick it in, it closes around it, and it'll go flat pretty soon. But if I was to stick it in the side, it pops right now. Okay? So, just magic is often science. Okay, let's let's try this right here. No, let's try that. Just let it warm up. I have a bowl full of beans, and these beans, nice black beans here, and I've got a steel ball. And this steel ball, if I put it in here, you think it will sink or will it float? Okay, now this is supposed to be a model of how water works, but it's not a good model because the beans aren't moving, so it sits on top there. If I set the beans in motion, then we'll see it sink. Okay? See, it disappeared right down there. There we go. All right. Change colors, right? Yeah, there's 2 of them. Okay? I got a ping pong ball. Stick it down below the beans. Cover it up. Not too deep or it doesn't come up for a while. I put the metal one on top. Give them a shake. One goes down, one comes up. All right? Let's do what are we going to do? The balloons and then we'll do that. Need the 2 balloons right there. We're getting ready for that one. I need one more. Let's see, it's right here. Sorry. All right, so let's try something else here. I've got in this bottle some beads, and they're blue and they're white. And if I sit it down here, they sort. All right? The blue beads go to the top, and the white beads go to the bottom. Hey, there's one white one was in the bottom. That's coming up. All right, so they sort out. Now what that tells you is that the white beads are less dense than the fluid. The blue beads are more dense than the fluid. So these sink and these float. All right? What do you notice about the fluid? How would you describe it? Is it clear? No. It's pretty cloudy, huh? But look down here. Is that clear? Yeah. What about up here? Okay. So we're going to let that sit for a second, and we're going to get ready for something else. I've got a couple of balloons here, and this balloon floats. Why does it float? Its density is lower than the density of air, right? So if I take this balloon, now when you buy a balloon, they sell helium balloons in the store, right? There's a reason they sell helium balloons and not hydrogen balloons. This is a helium balloon. If I put a flame to it, it pops, okay? And that's about all. Yeah, I'll have to get a relight. Now, let's try this one. This is not helium. Now, helium is the second element in the periodic table. It's got 2 protons. It's got 2 neutrons. Hydrogen has just 1 proton. So it's, the next one on the periodic table. However, helium is what's called a noble gas. It's non-reactive. Hydrogen, you can't say the same for that. Are you ready? So do you know why they don't sell hydrogen balloons in the store? Yeah, now you know, all right? Have you ever heard of the Hindenburg? Hindenburg was one of these blimps, and it had hydrogen in it, and the skin was flammable, and the whole thing went up and crashed, all right? That was quite a few years ago. All right, let's try this next one here. Thank you. Yeah. Let's see. Yeah. All right, so what I've got next is called a Van de Graaff generator. And a Van de Graaff generator is a static electric generator. It will produce static electricity. And I bet that, some of you people here are probably scientists at heart. You've probably done a scientific experiment with static electricity in your life. The one I'm thinking that you've probably done is the one where you rub your feet on the carpet and then you touch your friend. Yeah, you've done that one. Or you touch the doorknob, right? You get a spark out of it. Well, really, that's how this works. But this produces the static electricity for you. And it's got a belt here, like a big rubber band. That rubs down across the bottom, gets charged, comes up to the top, rubs across a different kind of pulley, and gives the charge to the top here. And so we should be able to see if we can get some sparks out of it. Let's see, you got to turn it on. Yeah, I got to turn something on. There we go. Not too impressed yet. The room seems kind of humid. If this doesn't work, wow. I usually get a much bigger spark than that, but we're feeling pretty humid in here today. And so this one may not work as well as it does at some points, but let's try a couple things with it. The first thing I'm going to do is take some peanuts here. And these are packing peanuts. And I take a piece of tape so it doesn't fall off. Stick it on here. And what I want to do is turn it on, and all of these should get charged up. If it's going to work, huh? Let's see if it works. That one's ready. Slow motion today because of the humidity. So water is a conductor. Okay, they all fell off now. That worked. Okay, great. Let's try another one, and I've got a metal cup this time. And so a metal is a conductor. And so, the question is, will the peanuts come out faster, or will they come out about the same as they did before? And we'll put 2 pieces of tape so we can get the metal touching right on there. Turn it on. Okay, a couple came off the top. And the rest don't seem to come out, all right? There's a reason for that. And it's the reason that you're safe inside of a car if you're in a thunderstorm. All right, this is a conductor, and all the charges stay in the outside of the conductor. None of them get to the peanuts in the middle. If you're in your car and your car gets hit by lightning, some people think, well, I'm safe because of my tires. Now, let's think about that, all right? Lightning bolt comes thousands of feet out of the sky, hits your car, and it can't get to the ground because of your tires. No, it just jumps from your car to the ground, all right? So you're safe in there because all of the charge is on the outside of your car, your metal car. Now, what happens when they make plastic cars? You'll be charged like the peanuts were, okay? I keep using this to discharge it. We're going to try another one, and then we're going to, this thing may or may not work. because of the humidity, all right? So let's try this and see how it goes. So I'm expecting limited success. It's sticking up a little bit. It works a lot better when it's dry. I think the ventilation's probably shut off in this room because of the humidity, the moisture in here. Okay, it's sticking up a little bit. If I take a sharp point and I point this at the hair here, I can make it go down, all right? Okay, let's turn it off. And let's try something else with this. So this thing is really a lightning rod. And I'm going to put it over here and see if I can get it to arc. Let's try it about like that. Okay, you can hear it arcing. Now I take my point. And it quits. That's how lightning rods work. They don't attract lightning to your house. They take the charge out of the clouds and you don't get hit by lightning. Okay? They stop lightning from happening. Looks to me like my Van de Graaff's going to die pretty soon. Let's try something else here. Now I keep touching it with this because this is grounded and it keeps me from getting shocked. I'm going to put a stack of pie tins on there. Hey, what can I say? That one seems to be a failure. We're not getting enough charge out of it. But we've got some other things that'll work. Let's we'll stop these. Okay. Well, let's go to something that'll work a little bit better. And what I've got is I've got a capacitor. Now this was a capacitor of sorts. This is a capacitor, and just hold that for 1 second. Let's see if we can charge this one up. Okay, so I'm going to take and sit this together, and I'm going to connect my ground to this capacitor and see if I can charge it up. So I've got this grounded. I'm going to turn this on. Okay, but I made a mistake here. All right, I got to discharge it somewhere. I need another ground rod. Okay, so I need to hook up another rod here. And we'll hook it up to this. All right. Trust me. Let's see if we can get this one to spark now. It's dead. All right, so let's charge it up again. Try discharge. Oh, that's real exciting, isn't it? This thing will store charge, but you've got to have some charge to get it to store. I can see my belt's coming apart on me, so that's another part of the problem. All right, let's see how bright it is. All right, a little bit brighter than you'd get rubbing your feet. Okay, now I need something here. This is an insulator. And I'm going to take this apart. I'm going to grab the middle of it. And I need a volunteer. Okay? I'm going to hand it right past you. Yeah, just grab that. Really, it's safe. I wouldn't kill you. All right. Okay, now I've got the rest of it here. And I'm going to take this apart. And let's see. You were volunteering too, weren't you? All right, I'm going to give you this part. And now what I want you two to do is just kind of give each other a high five. Ready? 1, 2, 3. Go ahead. Yeah, with your hand. Did you get shocked?
No.
Oh, okay. Let's have them back. Okay, so I'm going to hook this back up. I'm going to connect that to ground. I'm going to drop this cup inside. I'm going to take my little holder and put it back together. And then let's see if there was a spark there after all. Not much. All right. Okay, I quit with static electricity today. Static electricity is not my friend today. It actually stores the charge in the plastic. So it wasn't in the metal, it was on the plastic. Let's try something that I plug in. And so I have here a power supply. And this power supply... Okay. Lots of off switches. It says 148. Well, I can go 150 volts. This right here is a capacitor, and it's got some light bulbs. And when I throw this switch this way, it'll charge up this capacitor. So I charge up that capacitor. When it charges, the light bulb blinks for a short time. Once this hits 150 volts, then it won't charge anymore. You can see it's charging by this number. That tells you how many electrons are flowing in a given amount of time, and it keeps going down. Okay, now I'm going to shut this off. The next part has nothing to do with the power supply. This capacitor is charged. I can discharge it by throwing the switch, and the light bulb works. So you can store charge in a capacitor. Now if I use the other light bulb, well, they're both on that time. So let's just use the smaller one, and I will turn this back on. Charge it up, and that lights up. We're looking for this number to go down pretty close to 0, and it takes it a little while with this light bulb. It has resistance, and so it's resisting the flow, and it has more resistance than that one does. All right, that's pretty close. Shut that off, and if I discharge it, that dim light will last for a while, okay, longer than the two of them together did. All right, now if I wanted to store even more charge, I could add another capacitor. So I've got another capacitor here. That's discharged. And I've got to hook it up the right way, or bad things happen. Okay? All right, now we charge it up. What's not on? No. Okay, so let's see if we're a little bit loose there. Okay. All right, so shut that back. Let's see, discharge. Thank you for, I couldn't see the numbers there. Put that back on there and charge it up. You see the light bulb light up? Let's turn the other one on too, make it charge faster. And I'm waiting for that to go down. It's 60s, 30s, 20s, 10, 5. All right, so I can discharge that like this. And it didn't last very long. What about this capacitor? Oh, it's still charged, isn't it? And so I can discharge that. If I want to discharge it as fast as possible, I could just touch the two posts like this. Now this is a little bit exciting, okay? You had this light bulb lasted for a short time. One light bulb lasted for longer. And this is going to be the shortest possible. Are you ready? Okay, so a lot of energy at one time. Capacitors can be dangerous, and this thing scares me, all right? Now, the Van de Graaff doesn't really scare me. It's a higher voltage, but this one has current, so that one can get you, and I'll be touching it a few more times before I put it away, all right? Let's go ahead and get rid of this one. I'll do the bouncy ball. Thank you. Okay, here's another one that you could do pretty easily. I've got a ball here, basketball, and a bouncy ball. And what I want to do is I want to see which one of them conserves energy the most. Now, when I hold it up like this, do you believe me that it has energy? All right, so you've got your desk open. You put your hand on your desk. Okay, just put your hand flat on it like that. Now, if I was to drop, if I'm going to give you a choice, would you rather I drop this one or this one on your hand? This one, okay, why? Yeah, it's softer, and this one's heavier. It's got more mass. So mass has energy. Now, if I tell you I'm going to drop this one, would you prefer I drop it from here or here? No. Hello. You already know about energy. Has to do with mass. This is gravitational potential energy. Has to do with mass, and it has to do with height. So if I hold these up here about eye level and drop them, I'll see that it doesn't bounce all the way back up. It loses some energy. So let's test and see which one of these is the best. Which one bounced the best? Basketball did, didn't it? Okay. So is there any way I could get this one to go higher? Yeah. I could throw it down. I would give it I'd give it some energy when it started. What if I stack them like this? Yeah, it went higher. Now, did you notice what happened to the basketball? Okay, the basketball usually bounces about waist high. Let's try it again. So the energy from the basketball was transferred here and shot it way up high. All right, so you can lose some energy. Let's try another thing. I've got two. These look the same, but they're different. If I take this one and I drop it, It bounces fairly well, all right? It conserves energy, all right? This other one doesn't bounce. As a matter of fact, if I throw it, it won't bounce. And they call this a happy ball and a sad ball. Okay, I don't know. So you can lose some energy. I need somebody to help me here for a second. Come on down, just hold this. And just hold your hand out and hold on to it so it's not right. Come over this way. There we go. All right, now I've got two solid steel bearings. These are heavy. Okay, you can attest to that. They're solid steel. And when I bang them together, you can hear the sound. That's energy. But there's also heat produced. Okay, now if I hit them on this paper, you see holes in the paper? Then see if you can smell that and see if it smells like smoke.
Yeah,
it smells burned, doesn't it?
Burnt.
Okay? So it's burned. And we just pass that around. You can look at it. They're actually hot enough to burn a hole in the paper. Sure made a mess out here. Okay, so I'm going to try this one more time, but let's add a third ball, okay? So I'm going to put the tennis ball on top. Ready? Oh, I'm sorry. That didn't work like it was supposed to. And were you filming that as the ball came in? Okay. I'll try it again. I'll point a different direction this time. All right, ready? Got the camera that time. I've got pretty good aim today. Okay. I've got a pair of tennis balls here. Now, this is a practice. This is a demonstration that I've been practicing. And it takes a bit of skill. It's really not that hard, okay? Yeah, I can do it like this. It works fine. These have magnets inside of them, all right? I can stick them to the board here, and they have magnets. These have, how do you get the magnet in there? Well, you cut a hole, and you shove the magnet in there, and these magnets are rare earth magnets. They're neodymium magnets, and they will pinch you right now. They'll give you blood blisters, but in the ball, we can actually pass it around. If you promise to pass it back, okay, when we get done. Let's try something with magnetism. While you're getting that, I'm going to do this other one. So I've got an aluminum bar. Now, aluminum doesn't stick to magnets, does it? Okay? And I've got a steel bearing here, and if I drop this down, I'd expect in about half a second it's going to hit the ground. You ready? Sure enough, goes right through. The next thing I have is a magnet. This is one of those rare earth magnets. All right, it's a very strong magnet, and it doesn't stick to the aluminum. But if I drop it down in there, something interesting happens. Is it going to come out? There it came. Now, it was falling the whole time, but it fell really slow because as it falls through here, it produces electric currents. It makes electrons flow around the pipe, and that makes a little magnet which slows this down. Okay? These things here are held up with magnets. That's what sticks them to the board. And let's just try them out for a second. I'm going to put this up and let it go. They look pretty simple, but they're actually pretty complicated. They call them chaotic pendulums. And you can't make it do the same thing twice in a row. Okay? It's on. So we'll go lights in just a second. Okay, so I've got right here a big coil, and it's connected to power. And I've got another coil that I'm going to put on top of it. And if I turn this on, I should be able to see sparks. All right? So by putting this coil around the core there, I can make current flow through the second coil. If I drop that down, and I'll put another coil that has a light bulb on it on top, I turn it on, the light bulb lights up. Okay? Move it away, it goes out, put it down there, it lights up. I'm going to put the core all the way down. And just to make sure I'm not cheating, I've got a beaker here with water in it, and I'll put this in the water. Sit it down there, and it lights up. And you've got an underwater light bulb, no connection, right? Okay, if I put the core back up, and the simplest coil I could have would just be a piece of pipe. This is a piece of brass pipe, and if I put it on there and turn it on, it'll levitate again, okay? And what it does is it produces a current inside of here, and that current has a magnetic field. This has a magnetic field, and they're repelling each other. All right, now let's see here. Can you just fill that? It's hot, isn't it? So when you make the electrons flow through there, they crash into the atoms that make up the ring, and they make it hot. Now this one is aluminum, and it'll actually jump off, all right? But I've always wanted to go higher, so I built a bigger one of these. And we're going to see if the bigger one, if we can make it go even higher. I might be able to wipe that out now. All right, so here's a bigger one. It's the same thing, but on a grander scale. And I've got some different rings here. I've got a steel ring, and the steel ring levitates. Brass ring, wrong switch, will shoot up in the air. An aluminum ring. Now this ought to go higher, right? Okay, here we go. It doesn't go anywhere. Can you tell me why? What do you notice? Can you see right there?
Oh, it's open.
It's open. Okay, so you can't get current to flow around it because I took a saw and cut it. Okay, I've got one that's not cut. And we'll see if we can make that go higher. Oh, that went a lot higher. I didn't get the ceiling though. But it goes pretty high. Now remember how that one ring got hot? If you could lower the resistance, you could make it go higher. And if I cool this off, I could lower the resistance. I just happen to have something cool here. Liquid nitrogen. Anybody notice what happened to these beads? There are two kinds of material. There's actually alcohol and salt water. Two kinds of fluid. And so they separated. When it first goes, they're mixed, and that's why it looks cloudy. All right, I'm going to drop that in there and get it cooling off. I want to get it as cold as possible. And the colder it is, the higher it will go. Now, if it happens to bounce out that way, I wouldn't pick it up because it's going to be cold, right? We want to wait for it to quit boiling, so it's still boiling. Wisdom there, all right? Okay, it's almost to temperature. When it quenches, that's when it gets to temperature. It boils a little bit harder. Just about there. Come on, patience. You hear that? It quenched. It got to temperature. Now, I take that off. Stick it on here. You ready? And it went a lot higher. Still didn't quite hit the ceiling. I need a taller cart. Then I could hit the ceiling. Okay, now it's already warmed up a little bit. I expect it won't go quite as high this time. Still goes pretty high, doesn't it? Okay, and as it warms up, it has more resistance. And it goes just a little lower each time. There I go. I told you I'd throw it at you. Yeah, it's cold. Okay. All right. I'm going to do the stuff on this cart. Okay, so let's try something else here. Now, let's see. I can just use this power. Take less time. All right, I got a couple of light bulbs. But when a physicist is working with stuff, you never know exactly how it's been done. So these light bulbs are not very bright. They're 60 watts. If I unscrew one of them, they both go out. Okay? You know why that is? Yeah, they're wired in series. The current has to go through both of them. Unscrew it, it goes out. Doesn't matter which one I do, they go out. It's like Christmas lights, huh? One goes out, they're both out. I'm going to shut that off. And let's see here, hammer, plastic bag. We'll take this, put it over the light bulb. Okay, so let's get rid of the glass so we can see what's going on inside of the light bulb. Why do you need that glass anyway? Okay, we'll soon find out, won't we? All right, now as I turn this on, the filament, and you can see it, that's made out of tungsten. When it was in the light bulb, there's no air getting to it. Now there's air getting to it, and it burns. Okay, and it's gone. All right, I'm going to turn that back off for a second so that I can knock away the filament. And I'm going to turn it back on, but the light bulb doesn't light up because there's no way to get current to get across those wires. Now they go through the glass, but you know that glass is an insulator. Electricity won't go through glass, right? It usually doesn't go through glass. However, if glass gets hot enough, like perhaps with a torch, what we're looking for is to see if that other light bulb comes on. And I've got to get it pretty hot before it works. Now you notice this is orange because the current flowing through it's heating it up and keeps it hot. If I shut it off and back on, it'll still work, but if I shut it off and let it cool, it quits. Okay? I have another. This light, well, that one's really broken. I'm going to have to do another one. That got broke on the way out here. So I brought a spare light bulb, and we'll put this, unless I drop it again. Going to put it in this little socket, and put it in here. See if we can break it too. All right. The filament is still there. That's what I wanted. Okay. So if I plug this in and turn it on, it's going to burn up right now. But I think I can prevent that because I have liquid nitrogen, a physicist's best friend, right? That's really boiling. So this container is full of nitrogen. Nitrogen, you need oxygen to make this burn. It needs oxygen. So if I stick it, now let's let it settle down just a little bit. Okay. So I'm going to put this light bulb into the nitrogen and turn it on. And it doesn't burn because there's no oxygen down there. Okay? Still in one piece. But if I take it out, it burns up right now. All right. Did we miss anything on here? Oh, that's good. Okay, let's try the vortex cannons. Are we ready? Yeah, in a few minutes. Okay, I've got something else here. Let's see if I can help you out. This is just a bucket with like a drum on it. And, whoops, just propane. You're fine. It was just standing up there. All right, so I've got a bucket with a hole in the bottom and a drum head on the top. Are you ready? Did it get you? Okay, so it will shoot air out of it. Okay, so I push here and it forces air out the other side. Now that's kind of interesting. What's really interesting is that it will go quite a ways. And I'm going to set myself up a target here. So I've got some cups. And we'll put the cups out. Need a good target. Isn't that nice? All right. Now, it would be nice if I could see the air coming out of it. And I have, hopefully, yeah, it's ready, some smoke. Okay, so now I've got some, this is just smoke that you use, it's fog that you use like at Halloween. Okay, now we've got the cups over there. There we go. We still got a few minutes. Look around and see what we should do that we haven't done yet. look and see what we should do that we haven't done yet. How the candle doesn't matter. You'll have to grab those. Okay, now I'm going to put these two tables. Can you pull that one out a little bit? A little further? Perfect. It's just not sitting flat. All right. So anybody guess what the next plan is? Talk about something in physics called impulse. So if you have a force that's exerted over a very short period of time, you can make something interesting happen. I don't know karate. I only know physics, okay? You ready? Pretty good. The bottom two fell off. Not too bad. So I did that without breaking my hand because impulse. I did it fast. If you push slow, it's not going to break. But if you go fast, you have a lot of force in a short amount of time, you can break them. All right? Except the bottom two that fell off. I have here some beads, and this is one strand of beads. They're all tied together. And so if I take that and hang it off the edge here, there's weight on this side, there's weight on that side. It's doing fine, right? But if it gets far enough, if I go low, it goes slower. If I go high, it goes faster. Fast is nice. The bowl down there to catch them is so I can put them back in. You've got to very orderly put them in here if you want them to come out like that. All right? That's a lot like a siphon, but it's a bead siphon. Okay. You can take that one. Oops. You need one of them. Okay, I've got a spring here. And back up just a little more. I'm going to send a wave to Alinda over there. And it bounces and comes back. Okay, why don't you send one to me? All right, now let's make a really big one. Reach out there and make a big one. And let's do it at the same time on 3. 1, 2, 3. Let's go right through each other. It's kind of cool. I'll go up and you go down this time. 1, 2, 3. Okay. All right, now I'm going to send another wave just by... But let's see, if I do this slow... It looks a little like jump rope, right? Yeah. Okay, now what would happen if I did it twice that speed? Oh, I'm going 3 times. Too fast. Try a little slower than that. There we go. Okay, so I've got 2 bumps this time. Now let's try and see if we can get another one. There's 3. Okay. See if I can get 4. 4. So I have to go faster to make it work each time, right? I don't know if I can get 5. We'll try it. Yeah, you know, you could have people jump rope. Now we were up to 4 people jumping rope at the same time, but they'd have to be shorter people, right? Okay. How many? All right, I quit. What do we got next? Going to do a little bit of sound. So we're doing waves. Sound is a wave, and I've got a very simple musical instrument. This is an old film canister with some holes in it, and it's got a membrane that came from the grocery store because it's just part of a bag, okay? And I put it over a pipe. And the pitch that it makes is determined by the pipe. If I put a longer pipe on, you think it will be lower or higher? Was it lower or higher? It was lower. So let's try a short one. Now that's high, huh? Okay, so now I'm going to try a 4-foot one. Let's try the 6-foot one. It's all determined by what length of pipe you put on it. The rosin. Now this is just a piece of an aluminum, solid aluminum, and if I tap it, it makes some noise. But I think I can do better than that, and I'm going to put a little bit of rosin on my fingers. That's loud, huh? Okay, let's try it. Let's try a different place. So I'll try it. I've got it marked here so I can put it in a different spot. A little more moist in here. Higher, right? So shorter was higher. Okay, we about done? All right, so I've got a bottle here with a couple of screws put into it. And in the bottom, there's a little bit of a volatile liquid. It's rocket fuel of sorts. And I've got here, do I have a switch? It's okay. This will produce a spark. So I'm going to put this here, and I'm going to touch it. It'll put a spark across the middle. And what's going to happen to the volatile gas inside of there? Explode, right? You ready? That was exciting. Okay. You got something else? Let's do this swing one right there. I need the other part of it. Okay. I've got a little container here, and I'm going to put some, this is really just water, but it's blue so that you can see it better. And I've got a little tray to sit it on. So you know what the plan is, right? Yeah, we're going to spin it around, okay? I don't want to get wet either. No problem, right? Okay. Okay, I think we're pretty good. We got the... I think that, I pretty much did everything that I brought for you today. So thank you very much for having me come. Thank you for coming.